Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. Today we are going to discuss about sliding window filters in biomedical image processing. In previous lecture videos we have discussed about DFT, IDFT and Fourier transform and usage of filters in biomedical image processing applications. In this video we are going to discuss about the use of sliding window filters in image processing algorithms. Okay, in this part 1, first we are going to discuss about the linear image filters. Here, the linear image filters are mainly used to perform the discrete convolution. Here the equation is represented in terms of f of ij, it is equal to w convolution with h, it is equal to summation m equal to minus a to a, summation n equal to minus b to b, w of m comma n multiplied with h of I plus m comma j plus n. Here the function w is called a convolutional kernel or a filter mask, because in this linear operations first we have to calculate the resulting value in the output image pixel f of ij as a linear combination of brightness in local neighborhood of the pixel h of ij in the input image. Okay. See, here I'll give an exercise for you. Compute the 2D linear convolution of the following two signal x with mask w and extend the signal x with the zeros where needed. Here the x and w values are represented here in terms of array. Okay, normally we know that image smoothing is more or less equal to image blurring. Here, averaging of brightness values is a special case of the discrete convolution. For a 3x3 neighborhood, the convolution W is W equal to 1 by 9 and the rows and columns we have 1s. Applying this mask to an image results in smoothing. And we have MATLAB example program which calculates the local image smoothing effectively, and it can eliminate impulsive noise or degradations appearing as thin stripes. But it does not work if degradations are large blobs or thick stripes. See here the values of W, 1 by 10 multiplied with the array values, and W equal to 1 by 16 multiplied with the array values. Here the significance of the central pixel, it may be increased to better reflect properties of the Gaussian noise. Okay. Normally, we use image processing algorithms for perfect edge detection. Here, we have certain elements to calculate the edge detection. The first one is locate the sharp changes in the intensity function. Second one is we have to identify the brightness changes. And third one is we have to calculate the changes of continuous functions. And fourth one is we have to describe the gradients and the direction of the largest growth of the image function too, and finally the edges properly and the edge property is attached to an individual pixel and which is calculated with the help of a neighborhood pixel. And we have a vector variable, magnitude of the gradient and direction of the gradient. So we have to calculate both magnitude of the gradient and direction of the gradient to perform edge detection in image processing algorithms. See here the example image. Here the image which has the gradient direction and edge detection. First one, the gradient direction, it gives the direction of the maximal growth of the function from black to white. Here black it represents by 0 and white which is represented in terms of 255. And here the closed lines are the lines of the same brightness, and the orientation 0 degree, it points the east side. Okay, here the edges are often used in image analysis for finding region boundaries. Boundary and its parts edges are perpendicular to the direction of the gradient. Okay, here we have some typical edge profiles: step, roof, line and noisy. And here the gradient magnitude and gradient direction are continuous image functions where r, x, y is the angle in radians from the axis to the point x, y. Here the formulas are represented here, and See here, sometimes we are interested only in edge magnitudes without regarding to their orientations. So normally we use Laplacian operators. Here the Laplacian, it has the same properties in all directions and is therefore invariant to rotation in the image, which is represented as del square of xy, it is equal to dou square g of xy by dou x square plus dou square g of xy by dou y square. The Laplace operator is a very popular operator approximating the second derivative, which gives the gradient magnitude only. Okay, in this video we have discussed about the sliding window filters. The sliding window filters are used in the applications of image smoothing, which is normally equal to image blurring, and in this application we need to reduce the high frequency components first. Okay, after finding the direction of the magnitude and direction of the gradient and magnitude of the gradient, we use this algorithms for edge detection applications, because in image processing edge detection and boundary detection are the main element which is used to identify the edge and boundaries of cancer and tumor images for effective diagnostic and therapeutic applications. That's it. Thank you.